Proxy importance-based haptic retargeting with multiple props in VR. Haptic feedback is crucial for enhancing user immersion in virtual scenes, as it complements the visual information received. The haptic retargeting method redirects the user's real hand to the corresponding real object that provides haptics to the virtual object. This is achieved by exploiting the dominance of vision in human perception to trick haptics. In this paper, we propose a proxy importance-based haptic retargeting method with multiple props for dynamic scenes. Here is the video of two users playing chess in VR with our method. There are plenty of previous works on haptic retargeting. Asmantian et alia. Introduced haptic retargeting, which dynamically mapped virtual objects to physical objects, and also introduced 3 warping techniques. Matthews et alia. Investigated how predicting a user's target of choice based on gaze points can be combined with multi-physical prop mapping and on-the-fly retargeting techniques to reduce resets. Young et alia. Proposed that when guiding the user to place virtual objects, the physical prop can be placed in a specific position. The sum of the distances of the physical props from all virtual objects is minimized when the physical props are placed in this position, thus reducing the reset probability. However, these methods are still limited to static scenes, or high reset numbers, and long task completion time when retargeting. Our method can provide passive haptic with multiple props in the scenes containing moving objects. There are 3 steps in our method. First, we estimate the scene parameters, valid proxy distance and reset region radius. Second, we select the physical prop to move, and then haptic retargeting starts. Third, we select the prop placement location, and then haptic retargeting starts. In the first step, we estimate 2 scene parameters. First, we calculate the valid proxy distance with the binary search method. When verifying whether a given distance meets the definitional requirements, we record the number of virtual objects around each physical prop that are within the distance, then add them up. And if the ratio exceeds a predefined threshold, that given distance is valid. Second, we calculate the reset region radius. A circle is drawn with the midpoint of the virtual hand and the real hand as the center, and the distance to be verified as the radius. Then we sample uniformly on the circle and determine whether the retargeting process from the sampling point to the positions of the hands exceeds a threshold. If the ratio exceeds a certain threshold, that given radius is valid. In the second step, we first identify all the candidate physical props and calculate the proxy importance of each physical prop, then we select the prop with the lowest proxy importance. After that, the haptic retargeting process starts. In the third step, we identify candidate regions for physical prop placement and then discretize the region into placement points using wireframes. After that, we calculate the proxy importance for each point and select the location with the highest proxy importance. Finally, the haptic retargeting process starts. We designed 2 user studies to evaluate the performance of our method. The first one is with single user. We compare our method with 2 state-of-the-art methods. With CC1 method, when selecting objects, the physical prop that is nearest to the selected virtual object will be selected. When placing objects, CC1 maintains the relative positions between physical props and virtual objects without considering the distribution of other virtual objects. So if this nearest prop is the only prop around the other virtual objects, this can cause the other virtual objects to lose the nearby prop. As a result, the overall proxy closeness of the scene may decrease, leading to an increased probability of reset. With CC2 method, selecting objects is the same as CC first. When placing objects, CC2 selects a placement position for physical props that minimizes the sum of distances to all virtual objects. If some virtual objects are far away from others, the placement position might deviate from the concentrated region, resulting in a decreased proxy closeness for those objects located in the concentrated region. In subsequent interaction, this can lead to an increased probability of resets when moving those objects. In contrast, our method considers the distribution of all virtual objects when selecting a physical prop or placement position. We also exclude the influence of virtual objects that are far away from the selected virtual object or virtual object placement position. Our method has a lower reset number and less task completion time when retargeting. The second user study is with 2 users. We compare our method with 3 different ownership strategies. Green cubes are owned by the left user, and yellow cubes are owned by the right user, while cubes indicate the location of props, which are not visible to 2 users. EC1 is with strategy 1, which does not consider whether a virtual object is within the opponent's reset area or not. It results in virtual objects that are far away from the opponent, negatively affecting the importance. If the left user grabs the prop of a virtual object and places it in the most important position, and in the next interaction, the right user selects a virtual object which will cause the prop to be used again, then the right user needs to perform a reset, because the angle gain exceeds the threshold. EC2 is with strategy 2, which only takes into account the object owned by the current user. The left user grabs the prop of a virtual object and places it in the most important position, which is a bad place for the right user. Then the right user has to reset the hand to move the object in the next interaction. EC3 is with strategy 3, which is the weighted importance strategy. Different weights will be assigned to virtual objects with different ownership and locations. EC3 avoids the situation where physical props are distributed only around the virtual objects owned by one participant. This prevents the occurrence of local imbalances in the distribution of physical props throughout the entire scene, ensuring a more even distribution and avoiding local shortages or surpluses of physical props in the scene. EC3 has a lower reset number and less task completion time when retargeting. In conclusion, we have proposed a proxy importance-based haptic retargeting with multiple props to provide passive haptic for users in immersive VR applications. Compared to the state-of-the-art methods, our method achieves a significant reduction in the number of resets, task completing time, hand movement distances, and task load, and a significant improvement in usability without the cost of cyber sickness.